All right, ladies and gentlemen, let us begin. Things get a bit more complicated today, but still we are not going very deeply into whys and wherefores. My objective in this half of the module is to give you practical skills and explain to you the various terms and the little bit of physics that goes on behind it. So what determines the complexity of an electronic structure theory calculation is those integrals that we have already encountered in the previous lecture. Either explicitly or in some basis set they need to be taken, and they would broadly come in two types. One is straightforward expectation values here, so we've got one orbital and another orbital here, and then some operator in the middle. This is the momentum, in this case of electron 1, and this is all of its Coulomb interactions with whatever else occurs around it. And these are called one-electron integrals, and if we have n basis functions, of course there's one here, we will have around n squared of such integrals, and they are relatively cheap, and you can see the numerical complexity scales as n squared, so this is not too bad. The second type of integrals would be interactions between electrons. So you can see 1 over the distance, so that is a Coulomb interaction, then the probability density of one electron, probability density of another, except these orbitals might actually be different, all 4 of them, and therefore there are order n to the 4th such integrals for a basis set with n basis functions, and that starts to be difficult, because if you're having 1,000 basis functions, as you typically would for a small molecule, you're talking about 10 to the 12th integrals, which would tax a modern computer. So depending on how many of these orbitals are different, we can have what's called 1, 2, 3, and 4 center integrals. And because there are so many possible combinations of 4 orbitals, the number of 4 center integrals is very large, particularly in situations where orbitals heavily overlap. So for example, if you have one diffuse Gaussian in your basis that overlaps with everything in the molecule, it will create a giant number of 4 center integrals around it. And this is what dominates the costs of, for example, Hartree-Fock calculations. There are two types, particular types of these 4 center integrals that you will see in a lot of places. One is the straightforward Coulomb interaction. So look at this, this is psi I, so that is the probability density of electron 1. Then psi j is the probability density of electron 2, and these two electron clouds interact with each other with a straightforward Coulomb interaction. So this is literally just repulsion between 2 electron clouds at a distance. But you can have funny things which don't have such a straightforward physical interpretation. Notice here it's still psi I here, but the first one contains electron 1 and the second one electron 2. So this is no longer the probability density of any of the electrons, and in fact the physical interpretation of this is somewhat unclear. It comes out of the anti-symmetry requirements in fermionic systems, and for reasons of labels being exchanged like this, they're called exchange integrals. And you will see these types of integrals a few times here in density functional theory and in a few other places. Okay, so how do we deal with them, or rather how does the software deal with it? The options that you will see multiple times in Gaussian, games, Dalton, other packages that deal with that are broadly revolving around direct and semi-direct methods. In the dim and distant past, in the 90s and early 2000s, what was happening is a lot of packages would just pre-compute all of those integrals and dump them on disk into a giant heap. Now the advantage of that is, of course, you only need to calculate them once, and then you can simply read them as they are necessary. But the problem is, those days particularly, but even today, if you have a spinning platter hard disk, you would be able to access it at around 100 megabytes per second. And if it's a mechanical spinning platter, then the latency will be in the milliseconds. And that's really quite bad. The computer would spend most of its time waiting for the data to arrive. And for very large molecules, proteins, for example, the integral arrays wouldn't fit on the disk. But if they do fit, a good thing is you can compress it before you write it on disk and save some time. What emerged considerably later, so from 2005 onwards, this really became the dominant method, is to not even pre-compute and store those integrals, but simply recalculate them on the fly. Because all of those Gaussian integrals, as I mentioned in the previous lecture, are analytical. You could have a giant lookup table that is parameterized in sophisticated ways, and it's actually, given the latency and the access time and the bandwidth of realistic storage, it is actually faster to recalculate that integral, because it will happen in L1 cache or even the registers of your processor, than it is to retrieve it from somewhere else. So of course then your throughput is your memory bandwidth, and the latency is in the nanoseconds, because that's the wavefront velocity in copper wire, the time it takes for the signal to arrive from the memory banks. And so then we only need to store the basis description, which usually fits into the main RAM. Compression is not needed, but of course we would then have to form these integrals several times, because they might be necessary several times. Most packages that you will be using now in 2024 all default to the fully direct methods, unless there are some seriously complicated quantities in the post-Hartree Fock methods, which we will look at later in the lecture. There are semi-direct methods which recompute the cheap integrals and store the expensive integrals on disk. And this is something that is relatively recent, the last 10 years, right? The solid state storage has appeared. And of course, it's vastly superior to spinning platter disks. If you are retrieving a sector from this, you have to wait for the disk to physically rotate for that sector to end up under your reading head, whereas here everything happens more or less at the speed of light. Right, so latest PCI Express solid-state disks are recommended, and by all means avoid the spinning platter disks if you are even unfortunate enough to encounter the device these days. Even your laptops, if you open them up and take a look, do contain an M2 PCI Express solid-state disks on them. So mechanical used to mean high latency, but by now these devices more or less have been phased out. What else can we do with those integrals to try and reduce the numbers that we need to compute? The other term that you will encounter in the literature a lot and in the options of various electronic structure theory packages is called resolution of identity approximation. And the term simply refers to the fact that if you have a Hilbert space of functions and you have a complete basis set on it, then you can make an identity operator out of that basis set. So if psi n is your complete basis set, this will project the amount of psi n in your function that sits here, give you the coefficient, and then of course combine those functions back with exactly those coefficients. So that's an identity operator. What you can then do is observe that in a lot of basis sets that we have, the multiplicative relationships between basis functions are very straightforward. If, for example, we have plane waves, sines and cosines, if you multiply two sines or cosines together, you get a linear combination of sines and cosines, right? Your standard trigonometric relations. So a product of two basis functions is one or several basis functions of the same type in a linear combination. So we can actually reduce these products, and we can insert these unit matrices there to reduce them better. And for example, for two Gaussians, we know that a product of two Gaussians is another Gaussian at the center of gravity, or we can use another basis set and say that, okay, the product of our two basis functions will be a linear combination of the functions of some auxiliary basis set. What this means in practice is that these product relations become linear combination relations, and 4-center integrals are reduced to 3-center, 3-center to 2-center, And you can play those games in a combinatorial way and then reduce the number of calculations that you need to do. So a lot of modern electronic structure theory packages, either automatically or by user requirement, will use these auxiliary basis sets and these product relationships between basis sets to try and reduce the number of integrals that they need to calculate. Then, well, this was reasonably accurate, right? This is at least a controllable approximation. You can always either abandon it or have the exact linear combination here. If we go back to 1950s and 1960s, people didn't have that luxury. They had kilobytes of memory. They had to use punch cards. They had to store things on magnetic tape. And so one class of approximations, drastic approximations, that still persists to this day because it turned out to be quite successful for a lot of things. And this is something that your homework set begins with for today, is to simply just neglect some of them and parameterize some others. Because they are the most expensive part of the Hartree-Fock theory calculations, if we classify them into particular classes and just assign them numerically instead of evaluating them and fit those numbers to some experimental database, maybe we're going to succeed. Of course, these days this would have been pompously called artificial intelligence, but those days this was simply called semi-empirical, because instead of computing these integrals, we are replacing them with empirically determined parameters. And so in these semi-empirical approximations, the core electrons, by and large, are not even considered at all. Chemists have rightly observed that nobody cares about the 1s orbital in oxygen because it doesn't participate in any chemical reactions. It just sits there. So they're replaced by effective core potentials. They use minimal basis sets, so just one function per orbital, Gaussian or whatever. Some of them assume dramatically that basis functions don't even overlap, and so overlap integrals are dropped. Only the Coulomb integrals are considered. And then they ignore mostly 3 and 4 center integrals and parameterize the rest of them. And how they do it determines the quality and the abbreviation, as it were. And there's a large class of them. The earliest one, CNDO, complete neglect of differential overlap, really just ignored all of them. And then it started producing something that at least to physicists looked sensible, and so they were quite happy, until chemists pointed out that it was predicting flat ammonia molecule, which is a big no-no in chemistry. Of course, ammonia is pyramidal. And so then there's intermediate neglect of differential overlap, modified neglect of differential overlap, and so on. And you can see that as the history progressed and the indices have increased on this, the accuracy, right, so that's the average error in the hit of formation across an experimental database, you can see has gone down quite considerably. So that is for HC and O molecules, and this is for all molecules in a particular database. This is still not what you would consider chemical accuracy, but it is not ridiculous. In a lot of cases, you need some kind of guess starting geometry, and it is usually quite a sensible initial guess to save some time to do the initial geometry optimization using PM5 or PM6, and then start serious post-Hartree-Fock or DFT calculations from that geometry. And for example, the Hessian as well, because it helps with the geometry convergence. So your homework contains an instruction to use these first, PM3 I think, and then to proceed from that geometry. Now the practical accuracy of these things is sort of okay for HCNO. Don't use it for D or F elements, of course, and really as of 2024 or thereabouts, they're only good for initial geometry guesses and an occasional molecular dynamics simulation. But they are, of course, massively faster than proper electronic structure theory calculations. If you take strychnine, a sizable molecule, and you run geometry optimization, it will be completed in 20 seconds on a typical laptop with PM3, and it might take a few hours if you use Hartree-Fock method with a reasonable basis set. So for preliminaries, pretty good, and you will encounter a lot of them in the historical literature, particularly from the 60s and the 70s, when people really didn't have much choice but to use them. One particular thing that we need to take a very careful look within the Hartree-Fock theory is how it deals with spin. And the answer, of course, that it doesn't. If you look at this Schrödinger's equation, you will see that it doesn't actually mention spin. This is because in non-relativistic quantum mechanics, there's a complete symmetry with respect to spin up and spin down, because spin-orbit coupling only occurs in special relativity. And then we only have the Pauli exclusion principle that demands that we've got opposite spins in two spatially identical orbitals, but not much else besides. And so one reasonable approximation that once again you will encounter a lot in the literature and the options is to say, well, this is non-relativistic quantum mechanics, and so from physical reasons we know that the spatial part of the wave function for spin up and the spin down must be identically the same. That would save us a lot of calculations because, okay, two orbitals are going to share the spatial part, and so that is cheaper because there are fewer integrals to compute. It also has the lovely side effect that the wave function stays an eigenfunction of the total spin, and that is a requirement for non-relativistic quantum mechanics, so that is correct. However, not all of our molecules in chemistry are closed shell. You can have radicals with one or more unpaired electrons. You can have bond-breaking processes and situations where things do become genuinely spin polarized, and so this approximation would fail in that case. And of course, variational principle tells us that the more flexible the basis set is, the better the energy is going to be, so we will take a penalty here. However, within the non-relativistic framework, if we do allow different spatial parts for spin up and spin down, we run into a different set of troubles. Although it can now describe spin polarization effects in open shell systems, the wave function would not be an eigenstate of the total spin. It's called spin contamination. You would have mixtures of states with different total spin. And there may be stability issues, because if you start with a closed shell calculation, it might suddenly just, because of simply numerical errors, drop its symmetry and become unrestricted, so errors in magnetic properties. Now, because both are approximations, this is still Hartree-Fock theory, right? It's the mean field approximation, just two different fudges on top of that. Unfortunately, there is no general recipe here. For certain types of calculations, you need the restricted one, otherwise it goes wrong. For certain other types of calculations, you do need the unrestricted one, otherwise it goes wrong. And so there's a health warning here every time you are running calculations with open shell molecules for magnetic parameters. Certainly, you always need to check which one of these two is the appropriate one. I could never either remember or guess. In a lot of cases, the properties are accurate in one of these and dead wrong in the other, so be careful about which one you choose when the meta is likely to be consequential, usually when this involves spin magnetic properties or transition states. What about this spin contamination? Well, that's just the simple fact that our restricted Hartree-Fock orbitals must have a definite spin, because the molecule does have it, and the spin, of course, is just the difference between the number of spin up and spin down electrons in the electronic structure, then the same plus one. And there are various ways to improve accuracy, which you will be getting once you start reading the logs that, for example, Gaussian is producing. You will see it in your homework. So what you can do is simply just project out the part of the wave function that has the incorrect total spin. That's called the annihilation method. You can repeat this projection at every iteration of the self-consistent field within Hartree-Fock, or you can just introduce a penalty on the incorrect spin state. So during the wave function calculation, that penalty will be applied. And another health warning here: if you do have strong spin contamination, so the total spin does not correspond to what you expect, this usually means that Hartree-Fock theory is simply just not a good approximation. and you should be using something else, which we will discuss a few slides down the line. So in your homework, when you run the calculations, you will see the following kind of text in the log. This is all terribly technical, so the total energy, the convergence, on the density, various other parameters in here, but in particular you will see this s squared. So that's the expectation value of the total spin. And if we have a radical with one unpaired electron, it's spin half times the spin half plus 1. So we are going to have 3/4, so 0.75. And you can see that a higher spin state got mixed into this, but after the annihilation procedure, we are pretty close to 0.75 with a tiny error here. So if this is very far from the ground state spin that you expect for your molecule, then you have to start reading Jensen's chapter 4 because, well, it just hit the fan. Or talk to professional computational chemists who will be able to advise you on what is going on in there. The other thing that Hartree-Fock, being the mean field theory, does not correctly describe is electron correlation. So firstly, there are terms that correspond to excited states in the wave function that do mix into it that Hartree-Fock ignores. And secondly, there are simply just Coulomb interactions which moving electrons experience, and therefore they avoid each other as they move. So electron correlation in general in the literature has many definitions, but really it can be defined as all inter-electron interactions that Hartree-Fock approximation does not properly account for. So everything that the mean field theory fails to correctly capture. Static correlation is extremely important if you are breaking bonds and creating transition states. So imagine a situation when we are doing a restricted Hartree-Fock calculation. We start with a hydrogen molecule, so 2 hydrogen atoms, one s bonding orbital with 2 electrons in it. But because our wave function is restricted to have identical spatial part for the spin up and the spin down, the only way that the hydrogen molecule can break apart in that approximation is like this. So the 2 electrons must have exactly the same spatial location, just a different spin. But this, of course, is emphatically not how the hydrogen molecule breaks apart. You should have this. Right, that is the correct solution, so 1 electron on each of the 2 hydrogen atoms. And of course, for this, you either require an unrestricted Hartree-Fock calculation or preferably a calculation that accounts for both the ground and the excited state, which we will discuss in the next slides. So this static correlation is when a single population pattern of molecular orbitals is not a good approximation to the ground state. And so if you have bond breaking transition states, D and F element complexes, because D and F orbitals are very close together in energy, biradicals, large aromatic systems, these static correlation effects come into play and the Hartree-Fock approximation breaks down. The second case when it does is when you are dealing with accurate description of time domain processes. So for example, in elastic X-ray scattering, when a photon bumps into a surface and kicks a few electrons into the excited states and then scatters these X-ray as a result. So electrons would avoid each other dynamically, and this is again not captured by effective potentials because the electron only sees the average field of all the other electrons, not them individually. So van der Waals interactions, excited states, particularly magnetic and optical properties, would be incorrect. And so this more or less is the end, the nail in the coffin of Hartree-Fock theory. It was very important historically. It is a starting point of a lot of more sophisticated theories, so the reference state for perturbation theories, but it is virtually unthinkable these days that anybody would actually use it for production quality calculations. It is a starting point for better approximations, but nothing more than that. The last calculations that used it for practical prediction of anything was probably 1995 or thereabouts. Okay, so what do we do then? How do we account for these electron correlation effects? Another term that you will see all over the place, including these days, is Möller-Placet perturbation theory. And as you all know, physicists and chemists, perturbation theory is when we have some simple quantum mechanical problem with the Hamiltonian H0 that we know how to solve. And then we do know that our real problem does contain a correction, and it's a horribly complicated correction. And what is the simplest way to account for a correction if it's much smaller than the original Hamiltonian? Well, the answer was given by Rayleigh and Schrödinger, so it's substantially Rayleigh-Schrödinger's perturbation theory, but in the context of electronic structure theory, it's called Möller-Placet perturbation theory, and it's literally the same expression that you all know and love from your classical quantum mechanics undergraduate course. If we consider this to be the Hartree-Fock Hamiltonian and that to be everything that Hartree-Fock theory ignores, then we can run the perturbation theory with respect to that. I will not bore you with the details and technicalities here, but this is a sum over all excitations from the occupied orbitals to the unoccupied orbitals. They're called virtual in the jargon, and that's the standard couple of electronic structure theory integrals. And the difference between the ground state and the corresponding excited state, you have seen this many times in your basic quantum mechanics. But of course this is expensive, right? This is a double sum over all of the excited states, and so the complexity scaling becomes worse. Remember, Hartree-Fock was between n squared and n to the fourth, depending on how well you played. Typically these days, a naive implementation would have O(n) cube complexity with respect to the number of the orbitals, but even the lowest level of Möller-Placet has complexity O(n) to the fifth, at which point, if you have 1,000 orbitals in the system, goodbye calculation, right? It would become impossible. Higher orders are scaling even steeper, and MP4, if you do it over the entire excitation spectrum, is order n to the seventh, but you can probably restrict it for most molecules to single, double, and quadruple excitations in this sum, and then the complexity becomes order of n to the sixth. Typically, MP2 would account for about 80 to 90% of the correlation energy, so all of the effects that we've discussed in the previous slides, and MP3 would be close up to perfect. MP4 is very uncommon, used for high accuracy calculations, and so MP2 is the cheapest way to include those correlation effects to a reasonable accuracy, or rather, it's also diagnostic of the fact that you have strong correlation effects if there's a big difference between the Hartree-Fock reference and the MP2 correction to it. Be careful, MP is not variational. Perturbation theory, of course, is a deterministic correction. There's no variational treatment there, and so the energy needn't actually go down. In fact, in some cases, it can go up or even oscillate like that. It's not uncommon to get your Hartree-Fock reference energy. Then MP2 goes way down, but then MP3 goes up, MP4, and so on. That's an example for a beryllium atom, which is small enough to go all the way to MP7. You can see that's the correlation energy fraction recovery as a function of the perturbation theory level, and at MP7 you recover more than 100%. Of course, at MP8 it would get better, and so on, but of course the complexity of such calculations would be ridiculous. So in Gaussian, and this is something you will do as a part of your homework for this week, you can see Hartree-Fock, semi-empirical, MP2, MP4, so you can specify all of those levels of theory. In a lot of cases, for CH&O molecules that don't do anything complicated, like for example a protein simply needs to be folded, there isn't much of the electronic structure theory drama in there. These are excellent approximations, but in situations that involve bond breaking or excited states, it may well be that electron correlation is not a small perturbation. And perturbation theory, of course, requires it to be small, and at that point the theory would not converge. And so if you are seeing if the program reports convergence problems with Merle-Placid, that simply means that Hartree-Fock state is a very poor starting point because, for example, your molecule cannot be described by a single set of populations in a single set of orbitals, and we need to do something else. Right, what is something else? So this is the ultimate method, which when you take it to the limit, actually produces the exact solution to non-relativistic Schrödinger's equation. And so if we use this, then that's it, so far as non-relativistic quantum mechanics is concerned. What it observes is that the wave function in reality, of course, isn't just one population pattern, the way Hartree-Fock theory assumes it is. It may have contributions from an excited state and a second excited state and so on. So a linear combination of that and that and that and so on is the true solution to Schrödinger's equation. Like, for example, if you have allyl anion radical, you would have this closed ground state configuration, but you would have this excited state. And if you're looking at isomerization and other things and resonance diagrams, and here chemists know what it is, they are aware that you need to include these two, and probably also the spin flip situations here that produce a biradical character to this. So a situation when we do a true, honest, variational linear combination of all such situations is called multi-configurational self-consistent field. So the same as Hartree-Fock by and large, except we are doing it with multiple reference states. But of course, there may be very many of them, and that is the biggest weakness here. If we take into account every possible excitation, then the complexity goes from n cubed for Hartree-Fock theory to something like n factorial. And at that point, of course, you know that even 20 factorial is a large number, and so such calculations would be unaffordable, and this is called the exponential scaling wall in quantum mechanics. So what can we do? We can try and play various physical insight games. We can say, well, for typical molecules in typical chemical systems, electronic excitations are actually pretty unlikely. They are mostly sitting in their ground states. Maybe we need to account for first excitations, maybe second excitations, but triple, quadruple, and so on excitations are probably quite unlikely. This is called configuration interaction, and we take this multi-configurational self-consistent field ansatz and we simply just truncate it. We say, okay, our total wave function is our Hartree-Fock reference plus the sum over all first excited states, second excited states, and we vary these coefficients until the energy goes to the minimum by the variational principle. That's the correct solution. And if you take this to infinity, you will get the exact solution to Schrödinger's equation. And typically, for well-behaved molecules, if you truncate it at the second order, this captures 99% of the electron correlation effects as well. But unlike Merle-Placid, this is strictly variational. So all these abbreviations you will see once again when you start doing your homework. You can include double excitations, single and double excitations, single, double, and triple. The complexity goes steeply up. I suspect when you run this in your homework on your laptop, you will actually crash it, or at least it will overheat, or it will run out of memory or something. And of course, full CI is unrealistically complex, so astronomical number of configurations. It is really only in certain toy systems, or these days using seriously complicated tensor calculus that you can run full CI. Fortunately, full CI is rarely actually necessary in cases where you do know which set of orbitals is responsible for your correlations. You can just take those. This is commonly the case in D and F elements when you do chemistry of inorganic complexes. For D elements like cobalt, you know that it's the 5d orbitals that are responsible for what's going on in there, and so you just take that subset of those orbitals, do the CAS-SCF in there, and actually choosing those orbitals is a bit of a dark art, and this will be as good as a full CI. For F elements likewise, but this is something that most packages you will be using do allow you to do CAS-SCF, but that is seriously advanced stuff that will take you a while to get used to. Okay, a few more things that we need to look at when we start looking at configuration interaction. Of course, it's a variational ansatz, so the more functions in the basis set, the better. Unfortunately, with atom-centered basis sets, this creates two classes of artifacts. Firstly, if we include all single and double excitations and we put the two molecules together, and for example, we would like to know how strongly they are attracted to each other, we will create extra electronic structure excitations that weren't there previously. So you can excite an electron from this molecule onto an orbital that sits there, and the other way around. This is called a size consistency problem. So the sum of the two molecules would have the energy that is actually lower than the sum of the energies of the two molecules individually. This is because there's an extra variation of freedom due to these extra excitations. And so one needs to be careful about these effects, that in this case there will be an unphysical attraction between these molecules as a result of that effect. So this is something that configuration interaction suffers from, but Möller-Plesset perturbation theory doesn't, because it is not variational. Then the second problem is again coming from the variational theorem, but it manifests even in the Hartree-Fock level, called basis set superposition error. Again, we know the bigger the basis, the lower the energy, and if we bring these molecules close together, the basis set of this molecule will augment the basis set here, and so just due to sheer extra variational flexibility, the energy will slightly go down, and this will result in non-physical attraction. So the bottom line for both of these is when we are dealing with non-covalent interactions of this type, it is actually useful to use plane wave basis sets, because these problems only occur for basis sets which are local to each atom, and so you bring them together and the basis density changes and the description quality changes. Plane wave basis sets are uniform everywhere in space, and so they would not have those problems. Gaussian doesn't have plane wave basis sets, but CAS-STEP does, and so such calculations are better done on CAS-STEP. You can correct at least the basis set superposition error in the following way. You calculate the energy of the two molecules together, so let's call it a complex, but then you carry out two additional calculations which take into account the basis set superposition error. So for example, you have this methanol here and you have this water. And you know that apart from the genuine hydrogen bond in here, you would have the basis set superposition error. But it proceeds from the fact that the orbitals of water artificially augment the description of methanol. So what we can do is we can calculate this complex, but then we can calculate the energy of methanol with all of the basis functions of the water, but none of the electrons. And so this will automatically include the extra variational flexibility correction on methanol. Likewise for water. And so we've got this counterpose correction, which is the energy of this A in the basis set that includes both, plus the energy of B in the basis set that includes both, and then minus the energy of them individually in their individual basis sets. And so we would be able to find out what this delta E is. And the final problem in your homework set is to take two xenon atoms, or krypton, I think, in there. At the Hartree-Fock level of theory, there are no van der Waals interactions, and so the way these atoms, the only way these atoms can attract, because they're neutral noble gases, is through basis set superposition error. And when you start reducing the energy by optimizing the geometry, you will see that they come close together. So that's an example. And of course, the bigger the basis set, the smaller the correction is going to be, because the description is already pretty good if you take a really big and flexible basis set with polarization functions and diffuse functions. So if you take the fairly minimal one, you can see you've got 4 kilocalories per mole correction. That's an awful lot. That's almost as big as a hydrogen bond. If you take a bigger basis, it's much reduced. If you take a giant basis by these standards, it becomes 10 times smaller. This is because in a big basis set, we already pretty much are converged on the Hartree-Fock energy, and so extra variational flexibility adds nothing to that. So all of that is in Jensen. I've given you all of the chapters that are necessary. Read them when you have the time. This course is fairly relaxed in that you are assessed by the homeworks and the attendance. There is no exam in this module. So you will more or less absorb all of that as you're doing the homework, and just send me an email if Gaussian crashes. Those of you who are physicists, talk to the 2 chemists, because they had some of this in their undergraduate courses, and they would be able to spot obvious chemical problems that the physicists might not immediately detect visually when the molecule is drawn.